Welcome to the AGA's first webinar of 2025. Very pleased that you guys were able to join us here. My name is Mark Ballesteros. I'm the president of the AGA, and we're very happy to have you here with us. I am just going to share my screen and okay. So what we're here today is to get a presentation on the geothermal heating for industrial developments using an active groundwater aquifer in the Latrobe Valley of Victoria. Be presented by JORIK Poeesse and Martin Pujol. And I'll tell you a little more. Let's see, JORIK is a geoscientist with a background in structural geology and geomechanics. From Utrecht University. He's currently at Rockwater, and he's doing quite a lot of various projects in hydrogeology and in geothermal in Australia and around the world. And Martin is a hydrogeologist engineer, specialized in reservoir engineering and modeling for geothermal projects. He did his training from the School of Geology in Nancy in France and has a master's there. He's currently at JRG Energy, which is a global geothermal consultancy, and he is the direct use and reservoir lead there. So just tell you a little bit more about the AGA. The Australian Geothermal Association is the peak body for Australia's geothermal sectors, and we provide a forum for individuals and organizations interested in geothermal energy information, discussion, networking, support, and advocacy. We are affiliated with the International Geothermal Association, and we are promoting all aspects of geothermal here in Australia. So we're very pleased to have you here. You can see our website there. I encourage you to go visit. And on the right of the slide, you can see our corporate members, who we thank very much for their support. I just wanted to let folks know that from members, the video recordings and sorry about the typo there, and slides from the past webinar presentations, and as well as from this one, once we get it all up and loaded, are available to members via the website and also on the AGA YouTube channel. Last but not least, I just wanted to let folks know that one of the things that the AGA produces is a geothermal tenement map. The latest update is October 24, and that's now available on the website. The map provides a summary of all the licenses, applications, etc. in each state. And for members, there's also a QGIS project that has a lot more of the details, and you can download that and manipulate it as you see fit. So I will then, without further ado, turn this over to JORIK, who is going to be our initial presenter here. Thanks very much, JORIK, and take it away.
Can everyone see the presentation?
I can, yes.
Thank you. Well, thanks for the introduction, Mark. The presentation is quite on a specific project that we recently worked on, but the title that I've opted for is more generic: industrial geothermal heating in the Latrobe Valley, because it is also a showcase to how geothermal heat can be used for industrial purposes and transcending the usual applications for aquatic centers, as we, for instance, for aquatic centers, as we know here in Perth, or hot springs, as we know over in Victoria. So just some acknowledgements. This project did receive funding from the Australian Renewable Energy Agency as part of the ARENA's Advancing Renewables program. And then there's the necessary disclaimer that the presentation does not represent the views of the Australian government. So what we will be talking about is just a little bit of background on direct use geothermal heating and potential industrial applications. Then we'll move into the geology and the hydrogeology of the Latrobe Valley, the structural geology of the Latrobe Valley and the concerns that we had there and what sort of approach did we take to solve those concerns. A geological model was built, and then a subsequent geothermal reservoir or aquifer modeling will be presented by Martin. And then we close off with some of the engineering considerations and the conclusion. So just the background, so most may know, but in direct use geothermal heating, what we do is that we directly use the hot water for heating purposes. So you can think of applications like district heating, greenhouses, swimming pools, and this is mostly sourced from hot sedimentary aquifers. Essentially, you could do it from a shallow basement style project, but it's mostly, in practice, it's mostly sourced from a shallow sedimentary aquifer. The water is circulated through a heat exchanger and just fully re-injected. So we extract the heat and inject it back at a lower temperature. There are multiple examples of these type of projects here in Perth, where we have 13 aquatic centers heated by geothermal systems. There are several hot springs over in Victoria, which are direct use or directly use the geothermal heat and actually use the water directly. So industrial use of geothermal energy in Australia has mostly been focusing on electricity generation. So some are working on new projects, but there are examples, for instance, Birdsville, or in the Cooper Basin, where the focus of that was generating electricity. But using it for industrial purposes, it's already being utilized overseas, for instance, in the Netherlands, where it's extensively used for heating of greenhouses. So being in that shallower, relatively shallow sedimentary aquifers, typically working with temperatures that can range from 40 degrees for low temperature applications or 130 degrees when you're thinking about high energy, higher enthalpy applications. And given that a single doublet, so 2 wells, a production and injection well, could provide anywhere from 1 to 30 megawatts of heat. And if you put that in a financial, well, first an energy perspective, it's about 10,000 to 380,000 gigajoules a year, which you can use to usually displace gas if that's your primary source of heating. If you put that in a financial perspective, at $15 a gigajoule, I'm not sure what the current price is in Victoria. I've been out of the loop a little bit there, but at $15 a gigajoule, that's $200,000 to 5.7 million a year that you could save on your gas bill. Now onto the project in the Latrobe Valley. So what were the first application that we're looking at, industrial application, is a barramundi fishery. So an aquaculture project for growing out barramundi fish. And what these barramundi like is they like a constant flow of fresh water, and that flow is about 40 liters a second actually, or 3,500 cubes a day. And this water doesn't have to, not only has to be fresh, but also needs to be at an appropriate temperature, and that's about 30 degrees centigrade all year round. Now, Victoria is not, especially in winter, is not a very warm place, and the source water for this barramundi, for this in our project in the Latrobe Valley, is from a freshwater reservoir, which could be as low as 9 degrees. And to keep those barramundi happy at 30 degrees, we have to heat that water to 35 degrees to make sure that it's consistently 30 degrees throughout all of the ponds that have the fish in them. So if we heat from 9 to 35 degrees for 40 liters a second, that adds up to about 5 megawatts. And just to put it in perspective of the current projects, it's about 2.5 times the size of one of the larger Perth swimming pools in terms of energy demand. But it's not only a fishery here we're looking at. There's also very in near proximity. There's the plan to build an energy from waste plant. So it processes non-recyclable solid waste that would otherwise go to landfill, or essentially burning garbage and getting electricity and heat from that. However, that electricity and heat will be supplied to the local Maryville paper mill. If people are familiar with that, it's the Australian Opal or Australian paper mill run by Opal. So that energy, that heat left over from the energy from waste plant will be used by the paper mill. And to run that energy from waste plant, they actually need to preheat steam to 100 degrees at about 30 liters a second. So and that source is the same aquifer. So we're talking about heating 30 liters a second of water from 9 to 100 degrees. And that's a significant energy demand. If you would use that by gas, the gas bill would be huge. Now, jumping ahead a little bit, we won't be able to get a source of 100 degrees, a geothermal source of 100 degrees in this area, but we can get up to 70 degrees, and then we can boost the rest with a heat pump. But if you add this energy demand up, it's about another 10 megawatts. So the aquaculture and the energy from waste here in our location would total about 15 megawatts. And that would be the largest geothermal installation in Australia to date, as far as I understand, but please let me know if someone else has a bigger one. So now to the geology, because we first have to find a suitable aquifer to supply our geothermal heat. So where are we? We are in the onshore Gippsland Basin, formed in the early Cretaceous. It's marked by these southwest to northeast trending faults, creating depressions such as the Latrobe Valley, the Latrobe syncline here. And these depressions are tertiary depositional centers, and then bounded on the sides by basement rocks. And those tertiary deposits are mostly continental depositional settings. The coastline is a bit further out to the east, in those times. And there's a large coal province. There's a lot of coal deposits and fluviatile, interbedded with fluviatile deposits. It is marked by several unconformities as the basin transitioned to a more compressional regime in the tertiary, as we will see later on. So in terms of the stratigraphy, as I said, we have coal and sandstone deposits from the Eocene to the Miocene. And it's a major coal province, and some may know the Yallourn or Morwell coal formations. These are very thick formations that are actively mined in the area as well. And then we have our Burong Formation, also referred to as Traralgon Formation, which is actually which will be a target aquifer. And this is all underlain by some volcanics and the undifferentiated Struzeletsky group. As I said, the target is a lower tertiary aquifer, although we do have some additional aquifers. The upper tertiary, quaternary, the mid-tertiary aquifer and the lower mid-tertiaries. Now, why did our lower tertiary aquifer is the best target? It's obviously because it's the deepest down, but it's also because of all of the coal formations that are in there. In this Morwell and in the Hazelwood, there are very thick coal deposits. And what these coal deposits have done is, or are doing, they provide a thermal insulator from the heat flow from below, and essentially trapping the heat below those coal beds. And that's why we have in this region an exceptionally high geothermal gradient, and we find about 68 to 70 degrees water at 600 meters depth. And and we have proven that already. There is the nearby town of Traralgon. The Gippsland Regional Aquatic Center, again an aquatic center which is heated by geothermal heat from this Burong formation. So here's a little map before we dive into the structural geology. This is our location, and then we have our town of Traralgon and our offset or our existing geothermal project in the center of that. But the project in the center of Traralgon, if you look at the structural geology, was more in the center of this depression here, and didn't have that many concerns to do with structural geology. But our location here, further to the west, you can already see is close to a nearby existing or a mapped fault that was already mapped before we did our study here, and that caused an area of concern, because if it's actually a fault, it can potentially cause a barrier, and a barrier could have an impact on water levels of the aquifer at our location, and it could also have impact on the temperature or geothermal gradient in our location, and we'd have to make sure that we're confident about the temperature and also the water levels, and also the availability of this aquifer in our location. And especially concerning with a fault nearby a project, what happens when you start operating a geothermal project? As you start drawing from that aquifer and injecting into it, how does that fault play into it? So the workflow for this was to our best effort, identify the subsurface structures and geology from existing borehole and seismic data, build a geological model, and model the proposed geothermal operation. So I had quite some data available in different scales and qualities, and there's an existing geological model which was made for the coalfield mining in the area, as you can see here. But what is noticeable is that this is mostly all following each other. It's all connected, and there's not really a lot of attention given to structures. Are there any pre-existing structures? Everything is just continuous. There's also, we already had a local but simplified geological model that the University of Melbourne and ourselves done 2 years ago. It was also a bit less detailed than we would need for this model. We have the Victorian Aquifer Framework, which has surfaces for all the aquifers. But the issue with that is it maps aquifers and not necessarily formations, and it's really hard to distinguish any structures from that. And no attention was paid to structures in general in a model like that. And then there's the regional petroleum geological model, which does pay attention to structures, but it's mostly built out of petroleum wells, which are pretty scarce in the area. So conclusion was simply made: we have to make a new geological model. So this was made from a large amount of boreholes. There are many coalfield bores and varying usability for a geological model. They're actually quite detailed, but most of these bores are old, and the way they were mapped is a bit different, and it's mostly built on identifying clay interval or coal intervals. And the log typically looks like this. It's a coarse sand, medium sand, and then it says coals. That's what they focused on. So but all in all, it's a useful data set to pick tops for our formations. Local petroleum bores are useful, but they were, as I said, they were pretty scarce. They did have some velocity models for some seismic that we looked at as well, and they were particularly useful to make pics of the deeper basement and understand where the deeper basement is. And then on top of that, we had the local geothermal and hydrogeological exploration bores. So we of course had our local geothermal project in the town of Terelgen, and then there's a couple of hydrogeological exploration bores as well, but these were only a handful of data points. Additionally to the boreholes, so we had some seismic data in the area. We're hopeful that the seismic area, the seismic data close to our area, which is here given in green, would be useful, but this is seismic from the late 1950s. And unfortunately, that was not very valuable. There's no digital data available for that. It looks like this. It's suggestive mapping. It's very hard to distinguish and integrate that with other data sets. Fortunately, there was some seismic, as you can see here in the orange lines, a bit further out, but that was shot in the 1990s and reprocessed. And this was more interpretable with some examples here, although the left one isn't particularly great. This line from this 91A04 line was much better. But that said, it was still affected by the energy consumed by the coal members. As you can see, it's quite clear, quite hard reflectors in the shallow areas, which is reflections of all of the coal members, and then you lose a lot of energy as you go below those. But what we were particularly concerned about in this, with our nearby structures, are these structures forming baffles? So, as I already said, the coal model that we had, which is I've shown here, follows a folding geological model or slumping. It's a continuous stratigraphy over structures, so it would be a monocline, say. So if you consider that, and you start, so say our project is about here, so which it actually is, and we start producing from this red production bore here, then we can draw water from these intervals that go a bit shallower. Additionally to drawing water from the area where our injection bore is located. So we're drawing from both sides. But if we put a structure here, then we cannot really access, if it's discontinuous, then we cannot really access the other side here. And once you start pumping from this production bore, you won't be able to draw in water from the other areas, and you're drawing in more water from your injection bore. And your injection bore is your cold water, which you don't want reaching your production bore. So it would have a detrimental impact on the lifetime or costs associated with the geothermal system, either you get a premature thermal breakthrough, or you have to space your wells further apart with all sorts of costs associated to it. So the question was, do we see faulting along structures or discontinuities? And that's where we used seismic for to investigate. And what we can see here in the seismic, first of all, is this unconformity here, which is the basement, and then there's a second unconformity, which we mapped as the top of the Gurong formation, which we try to match. And then there's this potential structure here. You see this antiform forming, so there is some sort of monocline there. But what we see here, especially here in this red circle, is there it looks much more discontinuous. And if you move up along this discontinuity, it seems like everything is more connected. So based on this, and we saw this in another seismic line as well, is that the interpretation was that our older formations, so that is our Gurong formation, and as well as the basement, this is more compacted. And if you have a structure through that, or you have movement along it, it's more likely to be discontinuous and actually break. And if you, as opposed to your more shallower formations, which are less compacted and more ductile, so it's more likely to sink with it and slump over to accommodate the space. And so with that in mind, so we figured, well, there is a large chance that these aquifers are actually discontinuous. So what we took forward from this point onwards is look, all of these structures that we have we're just going to model them as if everything is discontinuous, including the upper intervals, as this is a more conservative scenario for our geothermal system, as we would be drawing in more water from our injection bore. So additionally, the seismic is really helpful in being able to map or get an understanding of the aquifer at our location, even though it doesn't run over our location. What it really shows here from south to north here, sort of a little bit offset from our geothermal bores, which are shown here, and the hydrogeological bore as well. As we know that the aquifer there is really thick, and this is in the middle of this graben. But what we see if we move north, you can see this on the seismic, it's significantly thin. So in the center of the graben, it's very thick. So towards the edges, it becomes much thinner. And that's unfortunately our location is also more towards the edge of the graben. So we see that significant thickness difference. And we see the same thing if we do some bore correlations over the area here, west to east, with our prognosed location somewhere in the middle, or just slightly right in the middle, as highlighted here. We see that thick aquifer here on our geothermal or our nearby geothermal well. And you see that we know that it's very thick, and we actually didn't even drill all the way into the basement there. So that's why the question mark is there. So, and then towards our location, unfortunately, the aquifer becomes much thinner. So that's something to consider for our model and our bore design. And this is a north-south correlation. So here, going from north to south, we see the same thing. It's consistently thin around our location, and then it becomes thicker further towards the south. So the aquifer in total was found to be about 50 meters thick at target location. Well, that's the prognosis, at least, with a net thickness of 30 meters. So we applied all this information, the borehole data, and the seismic data, and integrated that into a geological model. The model also includes the coal formations, to match the heat flow to the observed temperatures in the aquifer throughout the region. The approach that we took is we created a grid and dug inside with including discontinuities, so these faults, and using some of the seismic, which was a seismic interpretation, which was depth converted, and the formation markers. Create one grid for each interval, and then export this grid to Leapfrog to construct an actually explicit geological model, which is not typically what you do with Leapfrog, but that was the best approach here. So, as I said, the geological model then includes structural discontinuities, as you can see here. We've named that the Morwell fault, and then you've got your Loyang fault and your Long fault. And all of these structures are modeled with discontinuous discontinuities along the trace of the fault. Although some pathways around are still possible. Just show that discontinuity here. So this is what the model looks like. Then in the end, we have our Barong aquifer here, and then this Morwell fault. And to make it a conservative approach, we have a full offset of this Barong aquifer on the other side, much shallower, not connecting, and therefore not in direct communication across this fault. Just to highlight again that this is a conservative situation in regards to the reservoir model. So the final aquifer properties that the final prognosis for aquifer properties was depth about 545 to 608 meters below ground level, thickness, as I said, about 50 meters. Of that, only 30 meters net sand, so that is a little bit marginal, but we know the aquifer is quite permeable. The temperature was found to be upwards of 70 degrees. We had a historical production from the nearby deep water bores that helped us map that out. And for the ones that are interested, the water aquifer is actually quite fresh, very fresh, at 400 milligrams a liter TDS. And with that, I will move to JRG, is part on the reservoir modeling.
Thanks, Jorik, for this great geological introduction. So I've got a little bit of a visualization here of a number of elements. So there is the core model that Jorik's mentioned, one of the cross section that was drawn there. You see the digital elevation model, and in the background there is a reservoir model, and you can see that this reservoir model has a large number of vertical layers and varying resolution laterally, which results in a lot of blocks. In this case, I think over 300,000 blocks. Each one of those blocks can be attributed reservoir parameters, and the main one, permeability, controlling the ability of groundwater to flow from one block to another under a pressure gradient. So we can move to the next slide. And so what we have done for this project, we have adopted the workflow that was developed by the Geothermal Institute at University of Auckland. And this workflow essentially starts from a conceptual model built in Leapfrog Geothermal, which is essentially where Jorik's work finished, and then evaluates this geological model onto a mesh, a reservoir mesh, and then run the YWARA code, which is a reservoir modeling code, to solve the diffusivity equation and then predict the pressure and temperature in each one of those blocks of the reservoir mesh. And we first do that in what we call a natural state model, which is essentially the state of the reservoir before any production occurred. So that's the initial temperature and pressure in any block of that model. once we've matched the temperature and pressures with the known temperature and pressure of legacy wells that were drilled into this basin, we then move to a production history model, which is essentially matching the evolution of pressure and temperature over time during the history of production from when production first started following mining in the basin to today. And then once that's done, then we can move to our future scenarios, which is essentially continuing that legacy production and adding production from our geothermal production well and injection well, and then predicting how the injected heat depleted plume will travel in the reservoir, what pressure changes will occur, and whether the project is sustainable. We can move to the next slide. So the JORIK code has a number of capabilities. It was developed initially for high temperature geothermal projects, and for a low temperature application such as this one, we are using a number of those capabilities. The reason we thought this code had value for this project is the coal beds that JORIK mentioned are particularly low thermal conductivity. And he explained that this is akin to having a thermal blanket. And the gradients that can be reached in those core intervals can be upwards of 150 degrees per kilometer. So those sorts of gradients, we normally see that in volcanic geothermal projects, but rarely do we see that in sedimentary basins, where the typical gradient is 25 to 30 degrees per kilometer. Now, when you move out of those core units into sandstone intervals, the gradient drops to around those values. And what that means is the fluid properties, essentially the density and the viscosity, can vary vertically quite rapidly. And that in itself is leading to mini convection cells in parts of the model, and certainly advection movement of heat. So it's not entirely a conductive system as you would expect for a sedimentary basin, and having a code that's able to solve for that is critical. Some of the other capabilities of the code obviously is bringing in the complexity of the geology that's in the Leapfrog model. So chiefly in our case, the discontinuities across faults, and evaluating that onto our mesh, which is a series of flat layers with a high vertical resolution. So essentially it looks like a block model for a mining application. But if you go for a sufficiently low resolution around your area of interest, you can capture a lot of the geological complexity and bring that into your reservoir model. Can move to the next slide. So this is the workflow in a simplified cartoon. I've explained that we start from a natural state model, then move to production history, and then on to future scenarios. In practice, what will happen is you might have calibrated your natural state. So you have a handful of pressure and temperature data from legacy wells that were either very old, prior to significant production from the basin, or located in areas that were unaffected by production, certainly from a temperature point of view, and then you calibrate those the model against those wells. Then you calibrate the model by varying properties like permeability, like thermal conductivity of the rock. Then you move to a production history model where you start producing from the reservoir. So the production in the area has been primarily for dewatering of coal mines. There are a large number of depressurization wells within the reservoir itself to ensure there's no heaving of at the base of the coal mine pits, but also in aquifers that are located above our target reservoir. And because there is some vertical leakage, that that dewatering also contributes to pressure changes in our target reservoir. So we essentially run the same parameters that were adopted for natural state for production history. We check if there is a match. Generally, it needs a bit of tweaking. In doing so, what is necessary then is to then rerun the natural state. So you can imagine there's a bit of back and forth until you have a reservoir model that is consistent and is calibrating against both natural state and production history in a satisfactory manner. At that stage, we can be convinced that we have adopted a conceptualization, a parameterization that is that can explain the past and hopefully therefore explain the future. And then we can move to future scenarios. The code, the Waywara code is parallelized. It's optimized and runs quickly, but nonetheless, you can imagine that with 334,000 blocks, equation of diffusivity having to be solved for each one of those blocks with varying fluid properties as a result of those large geothermal gradient in places. The mathematical equations can be tricky to solve, and they need to be solved for natural state of a very long period of times until you reach a steady state, and for the production history of tens of years. So those models can be quite slow to run if you were to run them on your laptop. So what we are adopting for this is using cloud computing, in this case AWS, where the Waywara code is run out of a cluster, which in our case is 10 times 96 cores. Generally, we've only used one time 96 cores to run the model, and that you can see above a little table from Geothermal Institute demonstrating what that does to running time for one of their smaller training model. But essentially, this is critical for a project like this because it allows you to run the model more, hopefully get a better calibration, and yeah, not leave for the weekend hoping that your model will converge and arrive on Monday finding out it hasn't. So yeah, this was very, very useful. We can move to the next stage. So we'll start describing the model itself, the reservoir model. So the model has been rotated so that to be parallel to the direction of the through flow within the reservoir, with groundwater flow essentially discharging into the ocean offshore, and following I guess the general orientation of the basin, so that is exiting through this eastern boundary there. What you can see also on this slide is the elevation of the top layer of the model. So because this reservoir can be quite shallow in places, it is connected to the quaternary shallow aquifers in some areas of the model, and modeling rainfall recharge is important to achieving a satisfactory calibration of the temperature and pressure. So we have to model all the way to the surface and capture this topography. You can see on the right a table that shows the vertical resolution, which progressively increased to be highest in the area where the reservoir is present. We can move to the next slide. There was also obviously some lateral variation in the horizontal resolution and the mesh, the resolution being highest close to the wells that we were studying for this project. Boundary condition, I'll sort of perhaps not bore you with this, but just the main information is that there is in the east of the model at great depths, there is a natural through flow leaving the model, So that's captured so that there is not an unrealistic amount of recharge to the model if we were to set a constant pressure, or a slightly pessimistic view if we had a no-flow boundary, because this is obviously part of a much larger regional context. The other boundary conditions that do matter are those that are applied in the shallow layers of the model where the quaternary sediments are present. There's obviously recharge to those sediments, but there is also like a hydraulic gradient from west to east, which is captured there. And then at the edge of the model, we are introducing, within the basement, we're introducing constant temperatures from the warm hydrostatic model, and that is to provide some boundary conditions for solving the temperature and pressure in the natural state. We can move to the next stage. An interesting feature of this particular reservoir model, in the geothermal industry, we often use the intrinsic permeability, so in units of square meters or millidarcies or darcy. So you have Mr. Darcy the top right there. So this is a property of the rock itself, so it's intrinsic. Now, in the hydrogeology world and the groundwater industry, we often refer to the hydraulic conductivity, which is a parameter that is incorporating this intrinsic property of the rock of permeability, but also the properties of the fluid, the density and the viscosity of the fluid. And the reason that's done is that typically in the groundwater industry, the temperatures don't vary a lot, and it's reasonable to assume that the density and viscosity are constant, and that therefore there's a direct correlation between the intrinsic permeability of the rock and the hydraulic conductivity. And that just makes your life simpler. So that's why people do it. And this particular reservoir is located at fairly shallow depths because of those coal seams that do create good geothermal temperatures at shallow depths. It is being targeted for dewatering a coal mine. So for all of those reasons, a lot of the data that's available is coming from groundwater wells in the groundwater industry and is reported as hydraulic conductivities in meters per second, meters per day. So it is important to go back to what the intrinsic permeability is, so that the impact of the variation of the fluid properties with temperature are removed from that, and we're really characterizing the rocks properly. So this is just a little side note. We can move to the next slide. The other parameter of interest in calibrating the model is the thermal conductivity. This is particularly important in conductive settings, particularly important in this region because of very low thermal conductivity of the coals, which result in equivalent conductive gradients of 150 degrees C per kilometer, so very large gradients that you normally only see in volcanic regions. On the right side, you can see, courtesy of Hot Dry Rocks, a little cartoon that shows how that thermal conductivity is modeled in practice with rock samples. We can move to the next slide. So this is a cross-section through the reservoir mesh, which shows some of the discontinuities across what is interpreted in the conceptual model as the faulted monocline, some of the discontinuities in permeability that are resulting from that structure. And so that has a great impact because depending on the throw of that fault, this is obviously picked at a location where the throw is particularly large, you can have no connection between the reservoir west of the fault and reservoir east of the fault. And you'll see that this had a great impact on the temperature and pressure the natural state and obviously future scenarios. And in fact, it is consistent with what the temperatures near the project have been found to be. So we'll explain that in a couple of slides. So this is a series of offset wells for which we had temperatures. And this is the natural state calibration. So this is essentially showing what the temperature in the reservoir model is predicted to be at the location of those wells. And you can see that the little black dot is the data, the blue line is the model. And this is an acceptable match. This is an area where you don't see a lot of gradient change. And then if you move to, no, this is pressure actually. So that's probably why there's that much gradient. It's essentially the pressure match. And this is the temperature match where you see more of those gradient change, which essentially depend on the thickness of the coal units, which have the lower thermal conductivity, and the thickness of the sand-dominated facies, which have higher thermal conductivity and lower gradient. So yeah, this was the match at the temperature. We can move to the next slide. There's a great number of wells that could be used, and so this is showing sort of the calibration accuracy of all the wells statistically. So 2 degrees error within 2 degrees, and sort of in plan view some of those variations, which is very acceptable for a model of this type. Now, this is the resulting temperature in the target reservoir, and one of the things you can see, it's overlaid on top of the digital elevation model. So if you just go to next, yeah. So here you can see in the digital elevation model the various mines, because this is a current digital elevation model, where the topography is lower. There's been excavation. Then go to next one. We can actually even see in the DM some indication of the faulted monocline there. And what is very obvious there, once you've done that, you've displayed it, is there is a large temperature discrepancy across part of that structure. So, and more continuous temperatures across other parts. The position of the injection and production wells at the site as shown there. So within some of the highest temperature in the reservoir, even though the reservoir, the depth is shallower than the Gibson Recreational Aquatic Center, which is to the east there at 68 degrees. And if you move to the next one, Jorik. So these cross show like the fact that you have a temperature discrepancy across. It's an area where the fault is shown to have a large throw, and therefore the fluid cannot move from west to east, and so the advection doesn't contribute to the cooling of that reservoir locally, and the temperature of the reservoir is controlled primarily by conduction. However, in the south, the throw of that fault is much reduced, and essentially it looks much more like a continuous monocline. And so you can have some advection from west to east that contributes to a more uniform temperature across. And then the general through flow in the reservoir to the east. And so all of that is actually explaining why the legacy well close to the project is the hottest in the area, even though it's not the deepest. You can move to the next slide. Now, so that's the natural state calibration of temperature. The natural the history matching is mostly around the evolution of pressure within the reservoir. There is nearly 25 gigaliters per annum of fluid that's being dewatered from 3 coal mines since the 1967, and that's led to, together with offshore oil and gas, commingled brine extraction, this has led to significant pressure decline in the reservoir. And so this is what we needed to match in the history matching. So if we move to the next slide, you could see two of the key wells for which we had pressure data at different point in time. You can see how the modeled extraction at the mines has resulted to a drop of the pressure. If we look at the T286 monitoring well, for the example, from 60 bar to less than 50 bar. So it's over 10 bar pressure drop, which means over 100 meter a drop of potentiometric head in that reservoir. So very significant. If you move to the next slide. And finally, the question we had to answer was modeling continuous production and injection of the proposed production well and injection well designed by JORIK and his team. The depths are there, the separation is about 900 meters. And then the next slide will show us what it looks like after 30 years. So you see a cross section, the blue is the injection well, red is production. The target reservoir is a light blue with the basement contact and darker blue. And we can see the plume in section, which is nearly reaching the production well after 30 years. And you can see that it essentially has a cylindrical like a teardrop sort of shape. It's obviously there's some conductive heat resupply from the overlying layers, which is quite evident in the shape of that plume. And if we move to the next slide, this is the predicted pressure and temperature at the well. And the pressure is actually shown to continue to decline about 0.5 bar every 10 years as a result from the ongoing dewatering. We see the initiation of thermal breakthrough. So while we're not pumping the cold injection water, the temperature starts to decline towards the end of production, but are still very acceptable and suitable for this project. If we move next slide. And this is the injection well prediction. And so because the injection well provides pressure support, the drawdown at the well and the mounding in the injection well does reach a steady state. And the geothermal impact is not significant regionally. So the pressure is the pressure impact doesn't travel further than the distance between those wells, essentially. And that's kind of the conclusion. Over to you, JORIK.
Martin, I'll just conclude with that, just a summary of everything. I think you started off saying that there's a 15 megawatt thermal doublet possible, and the geology did confirm that the 15 megawatt doublet is possible at our location in Maryvale. The aquifer modeling that Martin just presented shows that the local structure and the groundwater flow seem to have not a significant impact on the development of the cold water plume, and the geothermal operation follows the teardrop shape. This allows for our proposed bore design of vertical instead of and Martin showed that had sufficient subsurface separation to prevent thermal breakthrough and wouldn't need to resort to deviating bores further out, saving costs on those saving the associated costs with that. The single doublet of about 100 liters a second and up to 70 degrees would be able to provide with 15 megawatts and would be the largest geothermal system to date in Australia. There's a couple of items we can't show, the life cycle costs, but we can say that they show for this business case a very positive payback period, even considering some significant surface infrastructure costs that would be associated with these wells, such as pipeline and the plant room infrastructure. With that, over to Mark. Mark is still here.
There we go. Sorry, having a little technology glitch with the unmuting. Yes, I'm definitely still here. Wouldn't want to miss the final conclusions. Thanks very much for that, Jorik and Martin. Very interesting project and very interesting presentation. Well done. We're pretty much at time, but we've got a couple questions here. What I am going to do here is you turn on people's microphones and let them ask the questions themselves. We had a couple questions in the chat, and I had all this stuff out to all right. Sorry. Just trying to, all right, I'm going to turn on I'm going to read the question here while I figure out how to turn on the microphones. We have a couple in the chat room from Bele Mino, who has said, sorry, he doesn't think that there's Burong formation in the onshore parts of the basin, only located in the offshore. The correct name there is the Turalagon formation. So I guess that's a comment, but he's got another question here, which is, what is the role of the geological structures for geothermal exploration and development in the onshore Gippsland Basin? Is there any chance of geothermal hot water coming along the fault or the flanks of the folded structures?
I can understand a part of this, and maybe I'll get Jorik to do from a geological point of view, but from a reservoir point of view, what we definitely saw is actually the reverse of that. So with that, potentially faulted monocline, one of the mines you would have located is in the south west of the model on the western side of that potential structure. And in the production history, we were actually finding that there were some temperature changes in some of the wells, and essentially the production for dewatering was causing movement across the fault in that particular area, because essentially there is a hydraulic connectivity across, or essentially not much of a displacement or not much of a structure, for lack of a better word, but not so much in the areas where the displacement, or I guess the absence of hydraulic connectivity is interpreted. So it was more in terms of preventing the lateral movement, rather than being an actual conduit like we may see in a volcanic context, because I think those faults, with soft sediments and things like that, can be subject to clay smearing and all sorts of things, and then generally they act more as a baffle in my experience rather than a conduit. In this setting, it's completely different in sort of fractured reservoir environments. But yeah, did you have anything to contribute to that, Jorik?
No, everyone can turn on the microphones, by the way, so be live if you want to comment on that directly. I think you answered the question there, Martin. I just want to comment on Burong formation is nowadays used also for the onshore portion. They changed the naming convention a while back, so that's why we're not talking about the Turalagon formation, but we're talking essentially about the same unit anyway.
Okay, thanks.
It's basically part of the Latrobe group, as far as I understand, and yeah, it's the same age. Yeah.
Okay, we might move on to the next question. We've got one here from Georik Poessse, asking, do you want to turn on your mic and ask that yourself? Asking how did you optimize the number of wells to drill?
So the target here was to try and get the flow with at least the least amount of wells as possible. So we are planning to do just a single doublet. We think this can achieve 100 liters a second, but we will need to make sure it has sufficient diameter, so it will be a sufficient, a reasonable size downhole and reasonable size completion hole and screens to accommodate for that flow, and also have sufficient pump chamber for the associated drawdown and injection pumps for the associated mounting.
Okay, thanks for that. And Asfia Nishat had some questions as well. Do you want to turn on the mic and ask those?
Yeah, thank you. So my first question was regarding the payback period of your project. My apologies if I missed it and it was in the presentation, because some part of the presentation I did not attend. So maybe in that portion you mentioned it. So what was the payback period in terms of numbers of years?
On the part of the presentation where I said that is that I can't disclose that, but it is very positive. It is a very positive payback period.
Sorry. Okay, yeah. And I was also keen to know if you had studied binary cycle or organic Rankine cycle for electrical power production also as a part of your feasibility?
So the added benefit of directly using the heat is that your efficiency is very, very high. Your efficiency in this project, where you could run a COP of 20, so your efficiency is nearly 100% on using you lose a couple of degrees here and there, say at least 90%. Whereas binary cycles for I mean, I know there's developments all the time, but I don't think you would be able to achieve an efficiency higher than 10%.
Yeah,
probably
not
even
even.
close
I'll
there.
just comment on that, because I think you would have seen from one of my slides that we're predicting that the reservoir highest temperature in the area of interest would be just a little bit north of 70 degrees, essentially where the project is located. And to my knowledge, one of the lowest temperature ORC system in the world in Chena Hot Springs in Alaska, so very low outside air temperature, so optimal condition is 160 degrees Fahrenheit, which is around 70 degrees C. So essentially the production of electricity with such low temperature is not viable in the Australian context.
Okay. The reason I asked was maybe that the requirement of hot water, yes, every industry has hot water, but if we integrate an ORC turbine and we first produce electricity and then after that we can use the remaining heat for the production of hot water, is this some viable thing?
Yeah, it's just not at this location. It's just not hot enough. Yeah, if you had 100 degrees C resource, or even that's a bit marginal, but 120 or 150 for sure.
Okay, thank you.
Thanks, Asifa. Okay, next we had one from Raghubir Rai. Raghubir, are you still here? Do you want to turn on and ask that? I'll read that out in case trying to figure out how to unmute things like I was. What can you say about reservoir performance over the long term, and how do you assess the long-term reservoir performance?
I mean, what we can say is we do in a way have a bit of understanding as to how this reservoir behaves because of the amount of dewatering that's occurred since the late 60s. So we know that since that time, there's been a very large amount of production out of the reservoir. So I think, I can't remember the numbers, but I think it said that amount is largely superior to the amount of production that we are hoping to get out of a well, and is also not coming with reinjection into the reservoir. So it's net abstraction. And we know how the pressure in the reservoir has varied in that period of time. So that in itself gives us a very good understanding of how the reservoir performs. I guess the the only uncertainty with this project is the impact of the structure and potential baffle impact. And by modeling the structure, as Jorik said, we are being conservative in that we're creating some extra pressure impact as a result of that no flow boundary condition. And so, yeah, but you might have missed that when I presented the permeability reservoir, but we're dealing with a very permeable reservoir. So the reservoir has got a typical permeability at a regional level of 1 Darcy, which 1,000 millidarcy, and then the available thickness is growth thickness 30 meters. So yeah, certainly quite a permeable reservoir.
Excellent, thank you very much. Let's going over to the Q&A section here. Ralph Opperman. Ralph, are you still here with us? You want to turn on and ask? You've got a couple questions for us. Well, I'll put it out there for him. So some of the faults mapped, for example, slide 16, he's saying, shows syn sedimentary activity with thickening across the fault, but the fault is shown as a reverse fault, suggesting a major fault movements over time and late compression of the basin. Has this been observed in the basin, basically the fault reversal, or given the scarcity and quality of the seismic data, are the faults maybe just all normal faults?
Let me just think about that question for a little bit.
Yeah, I did notice that as well. It looked like there was some thickening in the deeper section on the in the reverse sense. It looked like there was normal fault movement and then followed by compression later on and reversing things. So the high bit of the monocline.
So one thing to keep in mind is that the seismic that shows the faults is not the structure that we were interested in. So yes, you have a couple of structures here, but for instance, when I showed this one, this is not the structure that we were interested, that we are that is close to our boreholes, our planned boreholes, because there's simply no seismic of that. That said, are these all normal faults? Well, given the offset seems to be in a reverse setting, I'd say this is a reverse fault, but you could argue that there is some thickness variations in that, but that has not been very explicitly looked at on the seismic lines now.
Sorry, Jorik, I'm interpreting that question to suggest that it's was originally a normal fault that's been reactivated as a reverse
originally
fault.
A normal fault and being reactivated. Yes, but there is the change to the compressional regime in the tertiary, so that is possible indeed.
Okay. And another question from Ralph here. Have you integrated a geomechanical model for the area with the present day stress that may result in some faults with certain orientations that are parallel or subparable to the SH max being critically stressed and open, which would influence the flow, the fluid flow? Image log interpretations, if available at all, could potentially provide some evidence for this.
I don't think the faults will be critically stressed in the region, although we do have regional expression, but there's not really any historical natural earthquake activity, as to my knowledge.
The other context as well to this, I think, is we are essentially not relying on secondary permeability for that project to work. The target reservoir is a primary permeability reservoir, so it's naturally permeable. We don't need any fractures to make that a viable project. So in a way,
So
I mean, yeah, that's a viable question, but we're not targeting this fault zone in a way. We're targeting the reservoir away from it. Yeah.
And typically in sedimentary projects where you are targeting matrix permeability, that is the is a major form of that's the major conduit, and not any of these faults. And then there would be also be the discussion that still goes on: are these faults open, or well, our interpretation of this is if there is no offset, or if there is no communication between the aquifers across the fault, we're not going to expect fault flow through the fault, because there is no juxtaposition of permeable beds.
Yeah.
So just to clarify that from my mind, the fault boundary that you have in your model, you've assumed there's no flow across it.
Yeah,
we don't have to assume it. It's just that there's no juxtaposition of permeable units. Okay. There's no additional constraint. It's just that it cannot flow because there's low permeability on one side, high permeability on the other.
Okay. Thank you. And last, we've got one from Houston Herweischer. Is Houston, are you still here? You want to turn on and ask that?
Yes, I am. If the microphone works.
Yes, it does. Thank you.
Okay.
We hear you. Go ahead.
Well, I think Martin just addressed one of these issues. I had missed that. If there is complete juxtaposition, you would obviously have a barrier. I was just curious if you, because you mentioned it on this slide that you have to make a conservative assumption, but if you can sort of qualify that a little bit more by using well tests where you can or cannot see barriers.
That will be when we drill these wells, we will be able to test that and see if we see a barrier. So we'll start off with a stratigraphic hole and test that and see what we see on the well test. The crack wells, so that's the wells in the city of Traralgon, they have been well tested. I think Martin's probably involved at the time, and I don't think any barriers were observed there.
No, yeah, I mean the quality of the well test probably wasn't the highest, and it was very transmissive there, because I think, as Jorik showed on one of the section, the reservoir is thickening, and the local permeability is even higher than 1 Darcy for some of the sandstone there. So you end up with a permeability thickness that's sufficiently high for essentially and it was also tested at a much lower rate than the 100 liters a second we're talking about here. So yeah, we couldn't see any boundaries there, but it's also further away from those faults or potential faults. It remains I guess a hypothesis, but the other thing I would offer is that in calibrating this model in natural states, essentially the natural temperatures, we know there is a well to the east of that postulated fault, which is the hottest in the basin, so above 70 degrees. And to the west of the basin, where the reservoir is much shallower, the wells are much cooler. And so in the absence of that discontinuity, if you essentially allowed the permeability to be high enough for fluid to flow across, you could not achieve that, because you'd essentially have cold fluid moving from west to east and cooling down this anomaly. So the advection is strong enough to lower the gradients in places. So when you have cold water flowing laterally, it will reduce the amount of I guess the effective heat flow, for lack of a better word, that is observed in the temperature data. So you might still have the same amount of heat coming from the basement, but if you have lateral cold water flowing across, you would struggle to get this 70-degree anomaly at this particular location. So to me, that in itself is an indication that it's unlikely there's a strong communication in that part of the monocline from west to east.
Yeah, that makes sense. Anyhow, I hadn't realized. Yeah, so you're going to drill these wells, and then how far will this well be from that fault, roughly?
I think we're talking about maybe 800 meters.
Okay, well then, depending on the conditions, you might get an extra backup, but I think Martin's argument on the temperature distribution is pretty persuasive. Thank you.
Okay, great. I think we'll call it there. We're a bit over time, but good to see the interest in that. And thanks again to Martin and Jorik for that presentation. Thanks to everybody for joining us, and we will look forward to seeing you again at our next webinar. And yeah, thank you very much.
Thank you.
Thank you.
Thank you.
Bye.